Hello everyone. Good evening to all of you. As all of you know, we are conducting technical webinars with the industry experts from last few months, and this is our sixth webinar on performance-based design, rethinking structural safety and efficiency. So today we are privileged and glad to have Dr. Naveed Anwar, founder of CSI Bangkok and adjunct faculty in structural engineering at Asian Institute of Technology, Thailand. With over 3 decades of experience in research, consultancy, and education, Dr. Anwar is a leading voice in the field of structural design engineering. He has played a key role in the global promotion of modern design methodologies and has mentored thousands of engineers worldwide. So today, without wasting any more time, I would like to invite Dr. Naveed Anwar for his presentation. Over to you, sir. Thank you.
Thank you so much, Sandeep, and good evening and good afternoon to everyone who's joining this event today. Those of you who might have seen some of the previous webinars that we have been conducting also from our side, we have been talking about performance-based design quite a bit. And I think it is high time that structural engineers start looking at the performance-based design as an alternative to the traditional design. So today I will be talking about why we should be doing performance-based design and also a little bit more details about how it is done and how do we bring in other people and what's the main difference between a traditional design and the performance-based design. Can I see the screen? Can you please? Yeah. Yes, thank you. Okay, so today I'm going to start with a slightly deeper dive that we have done in our previous webinars because we have a little bit more time. So I want to discuss several aspects today. And we are going to look at performance-based design as well as the performance-based evaluation of existing structures. So both of them will go together. Now, the main reason that we look at a topic like this or even the design is to answer the question from the public, is my structure safe? And I have had this question from many people, from the public, from the clients, people who come to engineers and they ask us to design something and they say, can you confirm that my structure will be safe? And most of the time, we cannot answer this question explicitly because as engineers, we really don't have the answer. And this question actually goes back in history to the first laws that were ever introduced by the King Hammurabi almost 5,000 years ago. And he made a lot of laws, and one of them relates to structural, building design and building construction. So as you can see from here, the code or the clause says that if the builder is unable to build a house properly, and the house is damaged or falls down and it kills the owner, then the builder shall also be put to death. This is an extreme example of tit for tat kind of a law at that time. But as you can see, this is highly performance oriented. There is no excuse in this one, no excuse for design fault, no excuse for following the code, no excuse for construction fault. It's a straight way performance and performance not being met, and then the consequences. So this, of course, these days we have better rules, luckily for the structural engineers, but the concept is the same. And the reason we make a structure safe, we need to understand that very, very well, that why a safe structure is essential. Of course, we talk about the house not being falling, but it's much more than that, because basically we are trying to prevent disasters from happening. And disasters are a combination of three important parameters or concepts. One is the hazard, the second one is the vulnerability, and the third one is exposure. Hazard is what comes from nature or even man-made, and we have little control on that. The exposure is how many people will be affected, how many properties will be affected, what kind of industry might be affected. So that's the exposure, what is around that. So for example, if an earthquake comes in a desert, it doesn't really matter, no matter how severe it is, because there's no exposure to anything. But the important thing is which is the vulnerability. which is the inappropriate built environment or the lack of resources for communities. Both of them are vulnerabilities. So one vulnerability is that the built environment isn't good enough. Second one is the community itself is weak. They don't have the resources to do anything about the hazard. So once we do that, then this is the risk. So we are trying to reduce the risk. And because we cannot manage the hazard, we need to manage the. And that's why safety is to make the structure not weak, not vulnerable in a broader sense, and ultimately the disaster. Is everything okay? All right. Okay, so now let's look at the common hazards that lead to safety concerns or that lead to hazards. And they come from earth, water, air, and fire. That we are talking about today is primarily earthquakes. And we will also talk a little bit about the wind and cyclones or hurricanes because they are actually causing significant damage as well. And they are also related to, we'll mention that. So both these are the that we will be talking about, and others are also important, but not to be discussed today. Please let me know if there's any issue, okay, on time. Okay, so we're back. So what I was saying was that we are going to talk about three primary hazards. Earthquake is the main one, and we will also mention wind and cyclones a little bit when we do this one. Now, the design, the progression, if you look at the design from the history, first of all was intuitive design, which we talked about when the builder knew everything, and the design was based on experience passed from one to the other. And no real computations were possible at that time, long before math and physics were developed. But then after that, the building codes came in about 200, 150 years, 200 years ago, when we started to have formal computations or ways to compute structure. Okay, so we're back again. I hope we continue this time. So as I was saying, the building codes were introduced, and then they started to create rules for designers to use. And now the role of the building code is very clear. They are basically trying to ensure the public safety. And the reason is because a lot of people are now involved in the building process. There's the architects, there are structural engineers, there are contractors, there are builders, and so many people. So they want to make sure that at least a minimum level of safety is ensured in all structures, because each engineer may have a different level of training. So that's the reason to make uniformity and establish minimum standards, building codes are developed. And they basically give acceptable solution. They prescribe the details, how to use those rules. They also, give you exactly what formulas to use and so on. And they impose a lot of limits. And normally, building codes are developed from research and also from practical, application and experience. Now, the intent of the code or the spirit of the code is very clear. They want to give safety. And the intention is that if you follow the code, you should get a safe structure. Not must or you will, but you should get. So intent is to get a safe structure. If you follow the code, that's the spirit. But whether we really get a safe structure or not is not verified. After you design, you normally just finish the design and continue, but you never actually know whether the structure that you design will actually be safe or perform as expected. And that's the issue that the structural engineers are grappling with. So the modern codes, like I said, they will give you hazards. First of all, the problem starts with estimated hazards because they cannot give you the exact hazards everywhere that are drawn of the hazard maps, and they are quite general, quite broad, and then you use the numbers from there, and they apply to all the structures in that particular area. And then we define procedures for analysis and design. They also limit what structural system you can and cannot use. And then they also provide rules for detailing, which ultimately, for reinforced concrete and connection details, which for steel, they are the one finally governing the performance. So this whole procedure is followed systematically, and the intent is that this will give us a safe structure. Now look at, for example, some of the provisions. You get the limits, you get the spacing of the bar, diameter, spacing of the stirrups, and so on. Very detailed, but very prescriptive. The limits are, mostly rounded up, arbitrary limits on everything. But still, the intent is good behind this one, although the implementation may have drawbacks. But ultimately, the problem is that the engineers shelter behind the codes because they cannot answer the question that I asked earlier, will the building be safe? They can only say that I follow the code, but they cannot say that the structure will actually be safe or not because they haven't checked that particular structure. They have just followed the general procedures for the code, which are maybe developed elsewhere or copied from some other design codes and so on. So the problem, there are many other questions that the owner may ask. Most of them cannot be explicitly answered because we haven't done the real evaluation, and we will come to that in a minute. So let's look at the design for safety against seismic effects using the American approach as an example. Other codes are very similar, and see how they handle the earthquake. So for first of all, if you look at normal loading, for example, wind, dead load, live load, normally they are estimated and then they are multiplied by a load factor to bring them to a design level, 1.3 dead load, 1.7 wind or whatever. So we raise the loads up and bring them to a design level where we think is the yielding point of the structure. Earthquake is opposite. We start at a very not design the structure. Okay, so we're back again. I hope we continue this time. Somehow we are having difficulties with the internet connection today, unfortunately. So what I was saying was that the earthquake actual loading is far higher than the typically design level that we use. So we need to bring that earthquake, which is coming from the maximum considered earthquake or maximum credible earthquake, whichever way you look at it, which is an event which happens very rarely. We start with that, and then we bring it down to a design basis earthquake, taking 2/3 of that value, and that becomes the reference for the seismic design further. But still, it may be too high. So it is further divided or brought down to a design level using a response reduction coefficient or a response vectoring factor called R. And then we come to the design level. So you can see the difference here. One is loads are increased because the service loads are too low, bring them to the design for safety. But earthquake is already above the design level, way above, if you use the elastic limit or the yielding limit. So it needs to be brought design level. And we use the factor R over there in ACI code. Others have similar factors in the code. But the true response of the structure, the red color, is what happens when the structure is actually loaded beyond the yield point or its elastic capacity. So it goes up and then reaches a maximum value and then drops in capacity. So we do that. And now the challenge is to reach that top level of the red line, which we don't know through estimation. So then omega factor is added, which is the overstrength factor. And that is added because not all parts of the structure, see, you have overstrength, you have overstrength material, you have many factors we talked about in another web on this one. And then we get the net reduction from elastic to the nonlinear. And these factors can range from 1.5 to 8. You can see the variation. And omega can range from 1.5 to 3. So if both R and omega are equal, then we get in a linear elastic structure in which the structure has no way to become ductile and it becomes a linear elastic design. And that can happen in some cases. So that's the main problem that we are trying to, and codes have no idea what the real R is and what the real omega is. These are estimated. And the variation is so large that we get this whole gray area in which we don't know where each structure is. It could be anywhere between the lower level and the upper level because the R and omega can vary and this line can go up or down. So that's the main challenge, why we don't know the actual performance of the structure. We are just knowing the estimated value based on these factors. But the performance-based design does not do this. It takes these factors out and tries to estimate the actual red line. Once we have done the traditional design based on the factors, then we look at the capacity and demand. And then, for example, moment, we say that the capacity should be greater than the applied moment with some factor, which is in ACI is phi. In other codes, it could be gamma and so on. And then we say this DC ratio should be less than 1. So the codes are very straightforward. Less than 1 is safe, more than 1 is unsafe. But actually, real structure is not that you cannot decide exactly, because as you can see, the factors are so varying so much. So this value could be anywhere, and still the structure could be safe, or it could be unsafe, depending upon how we choose those factors in the beginning that we have mentioned. So as you can see here, to reach the MU or the demand and reach the capacity phi mn, there are many steps in between which involve so many factors, so many calculations, so many assumptions, so many factors before we reach demand over capacity. And that's the way the codes are set up. We just let the demand and capacity fight with each other, taking everything out. No phi factors, no gamma factors, no omega factors, no R factors. And even so, in the ACI code, if you look at the code itself, the acceptable region is the one shown in that colored portion. The theoretical capacity is somewhere there using the design values of the material, but actual capacity is much more than that, because the actual material values, material strengths are normally higher than the design values. So you can see that we are very far from the blue line, but we don't know how far, because all this is based on how the factors are chosen in various parts of the flow that I showed you. So, which means that we are away from the probable capacity, far away, but we don't know how far is that. So then comes the performance-based design. From the code-based design, the next step on the ladder is performance-based design. And I want to make it very clear what is the difference. When I was starting my career, actually more than 3 years before, than 40 some years something, at that time, when you want to specify the concrete, we used to write the value of cement, sand, and aggregate 1, 2, 4, and specify in the specification that the contractor will mix the concrete in this way. And then we expect that this will give us a strength of 21 MPa. But once we do this and the contractor follows 1 to 4, the contractor is relieved from responsibility of this strength, because we say just take 1 cement, 2 sand, and 4 aggregate, mix them together. And once he has done that properly, he doesn't care about the strength. And we cannot catch him on strength, because that's what we specified. But now these days, we specify concrete based on the required strength. And the contractor or the material supplier or the concrete supplier needs to deliver that concrete on site. If they don't deliver that strength, they have to bear the cost. So we have gone from prescriptive to performance in terms of the concrete strength definition. Same thing is happening with the whole of the structure. So now it is more about performance and less about conformance. So we say we don't care how you make the concrete, whatever you mix you'd use, it's up to you. Just give us the strength. Same is true now for structures. Give us the structure which has a certain performance. What factors you use, what material you use, how you do the analysis, what system you use is up to you, kind of. Of course, we don't have that much freedom, but ultimately we are required to prove that the structure is either operational, or it can be occupied immediately after the earthquake, or it will be safe after the earthquake, or it might collapse. So we have to work for collapse prevention and immediate occupancy as 2 levels. And of course, life safety is in between. And then the damage, estimated damage between that varies from 0 to 99% or 100%, if you can see that. And we have seen that the structure can actually collapse fully in the recent earthquake in Bangkok, where a building completely collapsed. So we did have complete collapse from an earthquake. So it's not not unthinkable, it's thinkable for that to happen. And so many buildings collapse, actually. So the second problem is that the prescriptive specification constrained innovation, because you cannot innovate if you are supposed to follow the procedure. There's no room for innovation, but performance indicators liberate the innovation. You can do whatever you like as long as you meet the required performance. And so the codes have this arbitrary implicit design level in between, which is not real. Because at this level, we don't know what the structure performance is immediate occupancy nor collapse prevention. So it's somewhere in between. But what we want is that the structure should not crack. It should be completely serviceable for a certain level of earthquake, which is service level assessment, for earthquake that happen quite often in the life of the structure, 1 or 2 times. And it should not collapse for an earthquake, which will happen rarely or in any case. So those are the 2 sides that we should check and confirm explicitly. And that's what the performance-based design does. So now if we do that, then owner has very clear control. Will the building be safe? Yes, we can do that and tell him, yes, for this earthquake, this level, this system, it will be safe and serviceable. Can I use the building after the hazard? Yes. In service level if service level is performance is satisfied, then yes, it is for a certain earthquake, it will be. How much will the repair cost, depending upon where we are on that graph that I showed you, and how long will it take to repair, we can also estimate. So then the engineer can do this and answer most of these questions. So that's the idea behind it. But because the engineer has a lot of freedom, we still need to make sure that the engineer is qualified, number one. Secondly, the design is checked, performance is reviewed by somebody who is equal or higher qualification or experience than the engineer. And there are guidelines to follow this process, not codes, but guidelines to help the engineer basically, because it's a complicated stuff. So now we just have the red line, the actual performance, and from MCE, we directly go to the performance for the collapse prevention, and for the service level, we go to the performance at the immediate occupancy or no cracking level. So we can just directly, and all R factors, omega factors, everything is gone. And that's how the performance-based design is supposed to work if we do it properly. And this is the procedure. If I can summarize it very briefly, you take the materials, nonlinear properties of the material, steel and concrete, including confinement and all, you put them in the cross-section, you generate the nonlinear response of the cross-section, like the moment curvature, you convert that into moment rotation, you create the nonlinear hinges or nonlinearities in the structure, and then once you have done all of that, you determine the realistic site-specific hazard, not the one that's given by the code, but you actually find out, and I will talk about that in a minute. You do the nonlinear pushover analysis or nonlinear time history analysis, and then you satisfy the key performance indicators, and then you get a realistic performance evaluation. So that's the overall scheme that we use for performance-based design. Of course, actual one is far more complicated, but the concept is here. And we can do this for a simple frame like this. And then we can plot the hazard and the performance together on one graph, the blue line coming from the performance that we did and the indicators on the hazard on the vertical side. And then we can see whether the disaster will occur or not, and what will be the level of vulnerability and disaster at different locations of hazard and performance level or displacement. So this is a displacement control mostly, plus the force control for some components. And now these are the 10 indicators that we can check, and I will show you how they're checked later. So stiffness, stability, strength, deformation, drift, ductility, damage, damping, energy, and acceleration. We check each one of them one by one to ensure that they're all okay. Once we have verified them all, then we have a lot of information about the structure, and we can answer a lot of questions that the code-based design will not answer or may not answer. So the code is then no longer a shelter, and from a performance-based design and performance-based evaluation then can answer the questions that we were asking earlier, because now the engineer has done a detailed nonlinear dynamic analysis with the real material strength, real hazard, with the real structure, removing the factors out of that. So that's the idea. So let's see what are the considerations for performance-based design. Now, going into the detail. So building codes, like I said, are prescriptive, and performance-based design has flexibility and innovation. So we already talked about that the prescriptive codes presume that it will be okay, but performance-based design needs to show that it's okay. There's a big difference between the left and the right-hand side. And this is, for example, a page from the ASCs, which limits the structure types, for example. So it says that if you're using a bearing wall system, you can only use up to that height. And if you want to go higher than that, you have to use a system with the shear walls and frame together, coupled together, where frames take 25% of the capacity and shear walls provide 75% of the capacity. And then you can go higher. So which basically means that if you are building like this, the code-based design will require that you must have the beams or a frame connecting to the shear walls, carrying at least, having the capacity to carry at least 25% of the lateral load. Whether you need it or not, it doesn't matter. You are required to do that. And then 75%, the walls should have the capacity. In a tall building, this is almost impossible, because in tall building, the frames are very few columns, very few beams. They don't have the capacity to carry 25% of the lateral load. They only have maybe 5 to 10% or less. But if you want to use the code, then you have to increase everything to follow that requirement. But if you use performance-based design, you can just simply use a flat slab, no beams, and then say, okay, I'm going to use a core wall and the columns and a flat slab. And core wall can carry all of the loading in this particular case, if we can demonstrate that. So that's the advantage of the performance-based design, that and that's why so many buildings, tall buildings these days, is earthquake zone, are being constructed by only core wall and no beams or no frame. So code-based design will require that, and performance-based design can prove that this can work as long as we do the whole thing properly. So that's one of the biggest reason why performance-based design can be used for tall buildings, but for low-rise buildings, similar things can apply. The other one is the omega. The code requires that some of the important members, like the inclined columns or the diaphragms or something, they must be designed for omega factor of 2.5 or 3 or whatever. So you need to have omega not of 2.5 over strength factor. That means the forces that you get, you need to multiply it by 2.5. The forces that you get from the linear analysis. But if you use PBD, you don't need these factors. You design them for actual forces that you obtained through nonlinear analysis. So that's the second one. The third one is that it allows you to use all kind of things in the building that the codes do not have any way of handling. For example, the dampers or outriggers, BRBs, and many other things. So viscous dampers and so on. So we can innovate in the building as long as we can prove that the system will work. So that's the key, advantage of using performance-based design. The next one, and very important one, is the requirements for confinement and ductility. So the codes will require that you confine the walls like this a lot. Like boundary zones have to be confined like this all the way, and also along the full height. But in practice, if you use performance-based design, you can actually reduce the confinement, because you can prove that lower confinement will work. So a considerable saving can be done in terms of the confinement if we can see that we don't need the confinement and we don't need the whole confinement over the whole height, because some locations are not yielding, so confinement is not needed. So that's another big advantage of using performance-based design. So what do we need to do this one? First of all, the basis of design have to be defined. Then the geotechnical investigations have to be done properly. Then more than the normal one. Site-specific hazard has to be determined. We cannot use the map provided by the building codes because you're not using the codes anymore. And also the wind tunnel test has to be carried out for tall buildings because wind demand interferes with the seismic the design. We will see that in a minute. For low-rise building, the last one may not be necessary. So let's look at the site-specific probabilistic seismic hazard assessment. So this is a typical zoning map, UBC 97 style, where we have zone 1, zone 2. Of course, they don't use it anymore. They use spectral acceleration, short period, long period. But I'm just giving you an example because many countries still use zoning to define the risk or hazard. This is no longer an acceptable way to do things in performance-based design. For that, we need to actually calculate the expected hazard at that site using all of the faults and sources of seismic excitation, their potential for all of the energy to be released and so on. So the whole analysis is done, and then we also find which is the dominant source, so we can see what is the direction of the fault, because that's also important. Which direction the earthquake is coming and which direction the building will respond. So after that, we need to get these at least 2 levels of response spectra and corresponding time histories. One for the maximum considered earthquake, which is roughly 2,500 years of return period, and that will be used for the collapse prevention performance. And then the service level earthquake, which is 43-year return period. So if the building's life is 100 years, it might come twice, roughly. And the other one is a very high risk. And this one will be the building needs to remain serviceable. Look at the damping. The design basis earthquake and the design codes normally recommend 5% damping to be used. For SLE, the damping could be as low as 1.6% because the service level demand is too less, so cracking would not occur. So building will be in a more or less uncracked state. So the damping will be low. And MCE, the damping could be higher. And then that varies depending on which specification you use. Sometimes they use 2%, sometimes 5%, and so on. So, but for service level, the damping is pretty low. And this has a major effect on the demand. And then the fault orientation is important. We design, when we model the buildings in ETABS or something, or any software, we think there's an X and there's a Y. But there is no X and Y marked on the ground. It is our assumption that this is the X direction, this is the Y direction of the building. But in reality, the building will be placed north-south and orientation with respect to north and south. And then the fault will have a certain direction. So seismic demand will come along and across the fault, normal and along. So we need to design both for the effect of the earthquake, which is along the fault, parallel to the fault, and effect of the earthquake, which is normal to the fault, once we determine the predominant fault. This is in Manila, for example. So if you do that, you'll have to orient the XY on your plan or ETABS with the north-south and the fault direction to find the predominant direction on which the building should be, or the seismic demand should be applied, or the hazard should be applied. So you need to input that data into whatever software you're using to make sure that the direction of the earthquake and the direction of the earthquake of the building, principal directions, are aligned for normal and along fault in excitations. And this is critical. Then level of earthquake, we have the service level earthquake, which, as I mentioned, and maximum centered earthquake. For service level earthquake, we check serviceability. Everything must remain elastic with a little bit minor yielding, collapse prevention. Everything should remain standing with a allowed deformation, yielding, lot of damage, but not collapse. Building may not be usable after that, but it must not fall down. So that's and it is controlled by limits on deformations, and as well as on shear in certain members. So you can see here that the damping is now controlled. Service level damping is controlled. 5% damping is for design level normally. MCR is 2.5 in this case, and then SLE is 1.6. So we control the damping now different from the code design because we expect the real structure not to have that much damping, and change of damping, as you know, changes the demand coming to this response spectrum goes up and down based on that. So that these are the critical things, and this depends on the height of the building and so on. So it's a pretty, not a single number can be used. So this has to be estimated properly. So how do we conduct the performance-based design? And many of these slides I have taken, from AIT Solutions presentation. Engineer Ong also may be joining today. He will answer some of the questions. So a lot of the work is based on the buildings which have been, evaluated by AIT Solutions at AIT, and we have borrowed some of these slides from them. So the performance-based design procedure is geotechnical investigation, probabilistic, seismic hazard, then selection of the design, schematic design, what system we are using, then wind tunnel for tall buildings, if that is the case, then elastic design for wind, and then nonlinear design for earthquake, and also elastic design for service level earthquake. So we can see the whole picture is very clear. And we follow that for doing the complete performance-based design of a building. 2 levels are checked. The design level is not necessary. So for modeling and analysis, for the service level evaluation, we create a linear elastic model. We use response spectrum analysis. We consider these things. Critical damping, generally 1.5 to 2.5%. Like I showed you, it's a range, depends on the building. Load combinations are very clear. We do not multiply the earthquake anymore because it's already service level actual loading. And then all of the factors, R, omega, and others are taken to be 1. So they are not needed in this analysis. Acceptance criteria is clear. The DC ratio should be less than 1.5 for deformation and less than 0.7 for force control. So we don't want any kind of shear failure or axial, or brittle failures. So this is, and the story drift is limited to less than 0.55%. So these are the acceptance criteria to ensure the building will remain serviceable after that service level earthquake, and it will be, it can be occupied immediately, so people can leave and come back after the earthquake. The MCE level, however, is more complicated, more comprehensive, because we use nonlinear model and nonlinear response history analysis, either pushover or full nonlinear, some full time history. And if you're using response history analysis, you use 11 pairs of ground motion, different, considering various types of, hazard types in terms of the near fault, far fault, and so on. So we make sure that we consider various types of time history characteristics that can hit the earthquake, the structure. And then the damping is less than 0.5%. And then we take the average of these 11 ground motions to calculate some of the things. And for some, we use average multiplied by a factor. And then we classify the actions to be either linear or non-linear. So the brittle actions, for example, are expected to remain linear. And the ductile actions are expected to be non-linear. So we classify them, and this is something that it may depend on the guideline that you're using and may have to be agreed with the people who will review the design and so on. But normally, this could be one of the things that we set up. As you can see, some things are allowed to be nonlinear, and the limit is on deformation, and things which are brittle, not allowed to be nonlinear, we check the force. So for the things which are going to be deformation control, we check the deformation at various performance levels, and then we make sure that the rotations, deformations are within a certain range specified by the code. And then for the force control, we make sure that they do not cross their failure point because there's no ductility. So that are the two backbone curves used to control the response or check the response after the analysis is complete. And normally, for a nonlinear time history, you will have the stresses, but we use the backbone curve already modified for the damage. So we use that modified backbone curve, check the rotation against moment, and we make sure that it is within the limits. Now, in this case, of course, we have to include the confinement effect in modeling, the nonlinear modeling. So if the portion which is confined, we use confined concrete curve, and portion which is not confined, like the middle portion of the wall, we use the unconfined. So even the outside cover is unconfined and the portion within the zone is confined. So we have to do a detailed modeling using fiber mesh or the, or even the nonlinear shell, whichever approach we use. There are many approaches. We have to make sure that we specify the correct model for concrete to take into account the nonlinearities and confinement effects. And once you have done that, then we can check the response more reliably. You can see here the response from the two types of concrete. And then I don't need to read this table. Then we have all these limits coming from different guidelines. These are coming from ASC. Different guidelines will be coming, different numbers may be coming from Euro, different may be coming from other codes. So this table has to match with the guideline that we're using. This is not code, this is guidelines. And it is subject to revision, in certain cases. So demand capacity ratio, there are two types. Like I mentioned, we have the elastic strength and we have the deformation inelastic. So we make sure that the two are satisfied independently of each other. Certain things for brittle, elastic limits, and for deformation limits. And these are the acceptance criteria. For example, for the beams, hinge rotation have to be less than the limit. And then for columns, the axial flexural interaction, hinge rotation less than that limit. Shear DC ratio for strength capacity and beam shear less than the strength capacity. So like I mentioned, for brittle, we can make sure that the strength, we do not have brittle failure. So strength is the primary concern. For flexure, where we have the energy dissipation, where we have the nonlinearity stored, we can allow more deformation. And same is the case with shear walls. And we limit for the shear walls, we limit the tensile and compressive strains because we can't really, the wall is so modeled in such a way that your rotation cannot be typically measured. So we check the strains at various locations. And then we have the limits on story drift, 3%, and then coupling beams and so on. So this is very important to set this criteria, agree with the client, agree with the guidelines, and agree with the person or engineers who is going to review the design. Everybody has to agree before we do this work. Then we look for global and local responses. Because now we are doing a very detailed model, very detailed analysis, so we know we have all the information that we need to make the right decision. And that information is a lot. Model analysis, base shear, story shear, building sway and displacement, story drift, shear wall strain, shear wall, shear capacity, frame member rotations, and so on. So let me see quickly what we can. So first of all, base shear. Very important to check the base shear from different analysis. Normally, when we do the performance phase, we at least have a linear model, response spectrum, and we have a nonlinear model, so we can compare them. We can also compare the wind demand there. We can also compare maybe pushover. We can also compare. So we can run many analyses on the same model. We can run linear response spectrum. We can also run linear time history if you want. We can run nonlinear pushover, and we can run nonlinear time history because the model is the same. And we can get all these base shear, and we can compare them. And the percentage is very important. And then we look at the transient drift. That means drift which will happen during the earthquake. And we also look at the residual drift, the drift that will be left after the earthquake is over, because building may not come back to its original state. And that's why the ground motions normally have to run longer than the earthquake for the building, to allow the building to come to a standstill, So let's say the ground motion, actual ground motion, 45 seconds. We may run the analysis for 2 minutes or so on until the building comes to a stop, and then see what is the drift at that last point. So we check both the drifts. We look at the lateral displacements. We look at the floor acceleration, is very important. We look at the strains in the wall, different points, different ground motions at all locations in the wall, compressive strain, tensile strain to be within the limit. We allow some tensile strain to yield, compressive strain never to crush. Then we have the story level shear not to exceed the capacity, the outline. We have the coupling beam rotations, make sure that coupling beams stay within the limit, rotation limit, and then we have energy dissipation to see how much energy was dissipated by what element, because ultimately it's the energy dissipation which will hold the structure during and after the earthquake. So we check all of that, where the energy dissipation is going, how many percentage that is. So now you can see it's far more than the code that we require. We don't just finish the design and stop. We go back and check everything to make sure that the performance is actually checked. So what are the tools of the trade? First of all, guidelines. So many different guidelines. These are not codes. As you can see, they're all saying guidelines, guidelines, guidelines. So these are the guidelines to guide the engineers for them to train them and then follow them. So many are there for tall buildings, different guidelines, low-rise building, different guidelines, and so on. So you must pick the right guidelines for your structure to start with. Second one is software. Very important, because the software that you pick should have the capability to do this analysis. In general, Perform 3D is the gold standard for performance-based evaluation. Almost all people running performance-based design would prefer Perform 3D to be used as a program. And of course, now the ETABS and SAP can also be used because they also have similar capabilities. So you can choose Perform 3D is more comprehensive in many ways, but also more difficult. ETAP also can do the same thing. It's easier to use, but we have to learn both the tools and see how they work. Then let's move on to the future direction. So the building codes are now trying to catch up. So they also recognize that people are moving toward performance-based design. So for example, in ACI, Appendix A now talks about performance-based design or nonlinear analysis. We had a webinar about this in a few weeks back. And then it says, okay, we will code-based design demands now from this one. They also consider that the wind could be higher than the lower wind because we may be dealing with, climate change and so on. So so the wind could also be brought down a little bit if it is too high to manage. So that's now another thing that codes are considering, high wind demand in tall buildings and also in region. So we have the pre-standards for performance-based wind design also coming up. And they allow now that we can do performance-based design for wind as well. So this is where the future is moving. So the difference between elastic and inelastic design is very clear, because things that you need to have a good elastic design are not good for an inelastic design. More stiff, more strength is not good, more mass is not good, more capacity is not good. So we have to the two are pulling the structure in two different directions. So that's why we have to create a balance between wind and earthquake. But wind and earthquake are actually quite similar if you look at it, because in earthquake, we have site-specific hazard study. For wind, you have a site-specific climate analysis. For earthquake, you have various earthquake levels, service level, dB, MCE. And for wind, we have various wind return periods and velocities. For earthquake, we have hazard response spectrum. For wind, we have wind force frequency domain data. For earthquake, we have ground motion time history. For wind, we have wind tunnel pressure in time domain that we can determine. So basically, two are matching if we look at it in that way. So we should be able to do the performance-based design for wind and earthquake in a similar manner. And that's what the future is looking at. So Appendix A code is going to seismic design up to performance-based. In 2025, wind is also going that way, the new code, as I mentioned. And then in appendix, we are also going to resilient and sustainable structures. So now codes are catching up on these approaches and trying to cover a broad range rather than only covering the code-based design that you used to do earlier, because so many people are now becoming familiar with these methods. So the codes also recognize that, and they're allowing these things to happen within the code boundaries. So now codes are no longer, they recognize, so they want to allow engineers to do more than traditional. So PBD and PBE is now coming in, and the codes, like for example, ACI Appendix A is also saying, okay, you can do this also without violating the code. So then we can move the seismic design all the way to resilience-based design, and we can bring the wind to performance-based and later to resilience design. Then consequence and risk-based design, as well as resilience-based design, is something that we will talk about some other time, but they're all derived from performance-based design as the next logical step. So let's look at how the PBD process is typically managed at a higher level. So like I mentioned, first of all, we have to identify which project is suitable for PBD. Generally, every project can be, if the seismic demand is high. If we're in a high seismic zone, it might be valuable to do that. We have to then convince the stakeholders that PBD should be done, because people, the building authorities, the client, engineers, everyone has to be convinced. Then we have to form a PBD team, then select the appropriate guidelines, a lot of difference which exists, then set up the performance indicators and criteria, consultation between everybody, carry out the need studies, all of the needed study, geotechnical, hazard, and all. Select the right tools, very important once again, and then conduct the PBD. So you can see here that it's not an easy thing. So many people have to be convinced and trained to do this. So challenge is convincing these stakeholders. And so we can see architect, start with the architect, that's structural engineering, PBD specialist, site-specific consultant, and PBD reviewer. So you will have to, the client will have to engage all these consultants and of course spend more money and more effort and more time to do this. It's going to delay the project in some cases because more work has to be done. So the client has to be willing to see that, and the client will only see that if they see the value in that. And like I mentioned, we have to demonstrate the value. For example, like I said, if the client wants to build a tall building with no beams for a better view or better clear head, they have no choice but to go to PBD. So existing structures, performance-based evaluation is very important because they're already made, so we cannot follow the code. We talked about that in another webinar. Retrofit needs can be reduced. Tall buildings not conforming to code limits can be designed, and structures with innovative systems can be designed. So this is some of the reasons why PBD can be selected. And then very important to understand nonlinear dynamic analysis. And we have been doing so many webinars on this subject because it's so important for engineers to be familiar. Having the right information, having the right software, and an ability to interpret the results. Tons of data will be generated, terabytes of information will be generated. How do you process? How do you, just getting the numbers out from that output is a task. And then you need a lot of patience because it can take months and months to do this right. So site-specific information, like I mentioned here, location, probabilistic site hazard, seismic input from the study, geotechnical information, all have to be done. And then, in a summary, we carry out the performance design as more than just structural engineers domain. It's not just structural engineers' problem. It's everybody's problem. The client, the building authorities, the architect, geotechnical people, everyone has to be on board. It requires extensive knowledge and ability to convince many stakeholders. And we, in AIT Solutions and AIT, we spend years, convincing people to follow that. It needs additional site-specific studies, needs specialist consultants and peer reviewers, needs additional knowledge of nonlinear and dynamics, needs special guidelines and tools, and needs skills and patience and understanding. So that's the summary of the whole performance-based design, as we talked about. And finally, we need to keep the big picture in mind. The first one is, what is the purpose of structural design? We started with safety. Safety is, we have to make sure that we have disaster reduction because we don't want to have risk for the disaster. How to achieve the design purpose? That's what we talked about, that, okay, you have to fix the performance levels. How to confirm that the design procedure is achieved, doing the nonlinear analysis and all of that, and checking everything that I showed you earlier. Then what if the design, there are two more steps to that. What if the design purpose is not achieved? What do we do? How do we fix it? How do we come back and improve it? And the last one, what should we do if the design cannot be, objective cannot be achieved at all? What is, do we go back and change the system? What are the things that we could do that it cannot be achieved? Do we accept the risk, or we distribute the risk, or what? So these are bigger questions in the whole process of the structural design. So with that, I think I'll come to the end. So I'll say thank you so much, everyone. And once again, our apologies for a certain delays in the beginning. So with that, I think we're done. Thank you.
Thank you so much, Dr. Anwar, for this amazing session. We will take few questions from the audience, and then we'll end this session. So, Mr. Ashish, can you see the Q&A section? Hello. Okay, let me read out. Mr. Ashish, are you taking over? Yeah.
I think you can take from there. It's fine.
Okay. Okay, sure. So the first question we have, what is the percentage of benefit if we get if we use PBD in tall buildings in terms of base shear reduction and sizing?
Yeah, so this question is it depends on a lot of things. The first thing is it will depend on the seismic risk at that location, and also it will depend on the wind demand because wind and earthquake, they sort of have an opposing effect. So if the wind demand is high and seismic demand is low, then you will have a different end results. And if the wind demand is low, seismic demand is high, then you will have a different effect. So it's very hard to quantify or generalize what will be the benefit in terms of the cost for any given or a general situation. It will depend from the location to location, type of structure. For example, if it's a shear wall building, the benefit will be larger than a frame building for a high-rise building. But the most important thing is that we can remove the beams from the system altogether, which makes the construction very fast, and it can reduce the height of the building. People, they can add more floors for the same height limit, and the construction time is reduced significantly, and we had the clearance is increased. So that advantage will depend on the system that we choose. So I think from our experience, we have found that it could be as low as, sometimes it may actually increase, because if the original design is not good, then it may actually increase, especially if the higher modes take into account. So it can be as low as 5% or as high as 10%.
Thank you. We have the second question. When we define performance level to apply on a building, which one of type performance levels satisfy and safe expected occur on the building and minimum percent?
Can you repeat that? It wasn't clear.
Yeah. It wasn't clear to me also. When we define performance level to apply on a building, which one of type performance levels satisfy and safe expected occur on the building and minimum percentage? Not sure about the question, sir.
I did not understand that.
Sir, can I take that question?
Yeah, please go ahead.
Yes, yes,
Go ahead.
yes,
Please
yes,
go ahead.
Mr. Anwar, please.
Okay, so for the code intended objective, the performance is actually for service level earthquake, the building should be serviceable. And for the maximum considered earthquake, the building should not collapse. So collapse prevention performance level. This is the basic code intended objectives. But this is like a minimum requirement. But if the client would like to have the better performance, for example, under maximum considered earthquake, they want to have the immediate occupancy higher performance level. In that case, we can also check and design by using a base isolation system or a damper system. So we can target for the higher performance level as well. So, but minimum performance objective is at least we have to satisfy collapse prevention for MCE level, and the building should remain elastic and operational under SLE level earthquakes.
Thank you, sir. We have a request from Ramakrishnan Sengani, sir. My request to Dr. Sir and Mr. Thong is the automation of NL hinges, nonlinear hinges for the RC elements. Although ETABS has the ability, this is not as accurate as when compared to manually calculated hinges from AAC 41 based on the outputs from SLE level. To reach the PBD in a larger number of audiences, we request there shall be a comprehensive course with some sort of automation, which will help engineers to pursue the most complex engineering. As Ramakrishnan, AIT alumni. So it's a request from sir to Mr. Dr. Anwar and to Mr. Ong. Next question we have, if the beginners start to PVD in his final year project, so which types of procedures need to adopt to achieve the objectives?
You mean in the studies? If somebody wants to do that as part of the
Yes.
study? Yeah,
Yes,
I think normally for undergraduate level, it might not be suitable to do this one. But if somebody really wants to do that, then I think pushover should be enough for a frame structure to study. I think that could be something that people can do, and people have done it. So they can understand the nonlinearity using a hinge model for a frame, and then maybe can then, of course, for master's program here at AIT, we normally do PBD as part of the thesis almost a lot, and do use time history and so on. Ong, you want to add?
Yes, sir. So if the student is a master's student to learn, if he wants to learn PBD, the first thing is he should learn the nonlinear modeling procedures, and also read the PBD guidelines, acceptance criteria, and the concept behind this. And another thing is for the nonlinear modeling procedures, start with the simple models like 2D frame or just cantilever wall only, and check the nonlinear response verify with the laboratory test results. There are several papers which are conducted based on the laboratory tests. We can get the hysteresis loop and the loading protocols of those members. And so the students have to model those setup in the finite element model and run it and apply the loading protocol and check whether the modeling procedure is close to the laboratory test results or not, to have the better understanding, and then go to the big building model. So that is important.
Okay, so we'll take the last question. I think there are two questions which are related. How can we perform a performance-based wing design? Can ETABS carry out this type of analysis? And what considerations should we take into account in the model? The same question we have, does Perform 3D help in performance-based wing design?
So can I start answer the question?
Go ahead. Yeah,
Yes.
go ahead. Okay. Yeah, sure, go ahead.
Okay, ETABS can handle the wind performance-based design. One thing is the computational effort. It is very intensive compared to the seismic design. For seismic PBD, we just run the ground motion at the base of the building, which may be 2 minutes or 3 minutes duration ground motion, which has maybe 5,000 steps to 10,000, 15,000 steps. But in wind PBD, we have to simulate for at least a 1 hour typhoon event for wind time history. That wind time history also applies not only one story. We have to apply for the tall building several stories. So the computational effort is very large, and handling the data is very big. This is one thing, but ETAPs can handle it. For Perform 3D, I think there is a limitation for the number of functions that you can apply, number of time histories that you can apply in the model. So you have to check if your wind time history and the program limitations, they are okay or not.
Thank you so much, sir. I think there are a lot of questions, but we are already. Can we take few more questions, sir? There are a few questions, I think.
Yes.
Yeah.
Yeah, we can take a few more, and then the rest. Yes. The rest you can send us, and then we can apply later.
Yes, sir. Sure. So I will take the last question for today. For Y column, which type of analysis is needed to for mitigating the torsion, and what should be maintained betterment? For Y-shaped column, I think someone is asking.
Y-shaped column, in the elevation or in the plan?
So I think it is in the elevation for Y column. Yeah, it's in elevation
yeah.
mostly. Yeah.
Yeah, sure. Yeah. So I think the problem with any inclined column and in Y also is that they will act more like a strut and less as a column, and their control may be axial force control rather than the bending moment or shear control as a traditional column. So I think any inclined column actually causes a severe severe stiffness change and nonlinearity change and where they're used. And they may have to be modeled as using the axial hinges, not only the deformation, because most of the forces in the inclined columns will be axial and much less bending moment. So the modeling, but most likely they should remain elastic. So we should not expect any nonlinearity from inclined portion or inclined columns
Yes, sir. For the Y-shaped column in PBD, we have to consider the particle earthquake effect. If there is an inclined column, we need to consider that. And another thing is at the joint, two inclined column and the bottom straight column, we have to consider the reinforcement, congestion, large confinement. So those things we need to take care.
Okay, thank you so much, sir. Thank you so much, Dr. Anwar, Mr. Ashish, and Mr. Ong for this amazing session today. And thank you so much, all the participants, for joining us today in this webinar. I think we can end this webinar for today, and we are looking forward for many such webinars in coming future with all of you. Thank you so much.
Thank you.
All right. Thank you, everyone. Thank you, Sandeep. Thank you, everyone.
Thank you so much. Bye.
Goodbye.